that's the thing with a small class. Always, one of you had a bad day, way off. Okay. So we will now, in today's lecture, we will start with descriptive statistics and data visualization. And again, we will use some options from R language. Okay. So before we do that, if you are, you know what is a slum test, right? A slum test. Okay. So what is the IV and DV? IV, DV means what? Independent. Okay. So what is the IV and DV for a slum test? What are the independent variables and dependent variable for a slum test?
Dependence, water cement ratio.
Water cement ratio.
Dependence,
Strength.
strength,
Workability. How do we measure the workability? The height. The height. Okay, so you can take the height directly. Height indicates workability, right? So we take the height, and she said water cement ratio. You want to add something in independent? Aggregate quantities, aggregate size. If you are using a plasticizer, would be compaction effort. Okay, how many blows you are doing? Method of compaction. Obviously, in a slum test, we have the same method, broad one, but in general it could be. Okay. So we discussed measurement of scales as well in the last lecture, right? So if my variable is type of failure, what measurement scale will this variable have? Type of failure. Nominal. What was nominal? True or false? Okay, good enough. Yes. Categorical. Is that categorical? But yes, it's the correct word. Okay. What R function shows you the structure of the data? There was a STR. Yes. Okay. So it will show you basically that what type of data. It will not give you many values, but it will show you the type of data. Okay, now we move today towards describing the data. Okay, so we need to describe the data in terms of the typical value of the data and the spread of the data, variation in the data. We want to see a normal value, and we want to see how far it can go. Okay, and interestingly, this is the same topic I am covering in the traffic engineering course as well in this week. Okay, so sometimes it goes like this. So typical value is normally in the center of the data, and the spread is the range of the data, the minimum, maximum standard deviation, and these things. Okay, so we want to understand these two main items. These are two main items we need to understand about the data. Okay, what is a typical value of the data and how far the data is spread out. Okay, it's very important for research. It's very important for analyzing the data. Okay, and in some cases it will help you to decide the measurement scale. Okay, so if a data is only 0 and 1, obviously we know the measurement scale is nominal. Okay, if the data is 0, 1, 2, 3, 4, 5. Ordinal, right? And so on. So, if you once you describe the data, then you can select the type of variable you have and how you will use it in the analysis and so on and so forth. Okay, and the typical value, and both these things also help you to decide the accuracy of your measurements. Okay, I was talking about the traffic course, and some of you. When you did the traffic code, you did the speed studies and so on, right? I don't know or defiltrated and covered? We did. So where did you do it? Load parameter.
Just on the previous page.
Very good. Very honest. Now you can say. Okay. So, but the point is, if somebody took the speed values, now they are showing the speed of 200 kilometers per hour. Okay. So we need to understand these things. We need to look at these things to see if the data is valid, if it is accurate, if there is any mistake, if there is any calculation error. We will know from this. These two items are very important. Okay. Another point about describing the data is they use a very good term in the traffic book which is called as data reduction, reducing the data. Okay. So when you do the descriptive statistics of the data, it reduces the data to some representative values. So I may have 100 values. If somebody asks me that what data you collect, I can throw all the 100 values at that guy, see what do I have, or I can tell him, okay, the values I have are around 50 kilometers per hour, okay, and they go from 30 to 80. Much easier to understand, right? Much easier to communicate. So the data which is described and it has descriptive statistics is reduced to a smaller set of representative values which tell you about the main information about the data. Okay. And this I already mentioned that once you look at the values, you can see if there are any errors. You can also look at the outliers as well. What is an outlier? Anomaly. Okay. Meaning what?
Something out of the data range. It stands out.
Yeah, it stands out. Okay. Something which is out of the normal range. Right? So there are different methods to identify the outliers. You may also, if your data consists of more than one variables, like we gave the example last time, strength and slump test. So there are more than one value, right? But we know there's a relationship between the values. Okay, so you can see the patterns as well. Before you start doing the analysis, you can see if there's a pattern or not. Okay, when this thing increases, this thing decreases or not. For example, we have traffic accidents data. The pattern in the accidents is normally fatal accidents are very low, others are very high. The accidents have deaths are very low, others are very high. So the ratio is less than 10%. Okay, or less than 10% are fatal, the others are very high. Now, if I perform any normal analysis with this data, you said outlier. Now, if I have 4,500 something accidents which are not fatal, they have injuries or something, and then I have very few, 300, 400 out of the 5,000 something, more than 5,000, only 300 something fatal. Okay, does it not look like an outlier? It looks, right? This is the outlier. But we know I cannot take it as an outlier. If I take this as an outlier, the most important thing is gone out of the data. Get the point? Okay. So you need to understand the patterns, the trends. Another thing which we saw was that, for example, we had the weather data. You know the weather data. But they were categories of weather data. In the record, they made categories. Okay? But when you look at the data and you do some descriptive analysis, you will find that the other categories are almost none. Most of the time, it's bright sunny outside. Okay? So now, do I need to have this variable in my data? It will not have any effect, right? So, descriptive analysis has to identify the errors. It has to identify the outliers. You can decide then whether you want to keep them in the analysis or you want to clean your data. We call that data cleaning. In some cases, we don't want the outliers. The speed data. I don't want the outliers. There was one crazy guy who was going at 160 kilometers per hour or 180 kilometers per hour. I keep him in the data or her in the data. I don't know about you guys. So if I keep that one car in the data, it will destroy my average, right? So the normal average is 50. Because of that 160 value, this will go to 52, 53 maybe. Okay. So now then you decide whether you want to keep the outliers or you want to clean the data. And the next thing is, the most important thing is you see the patterns before you start the analysis. And once you start the analysis, once you have the model, you have done some testing and so on and so forth, then you can check if your analysis is correct or not. If your analysis is correct or not. Okay. The data was showing one thing, the analysis is showing something else. That means there's a problem somewhere. Either you made the analysis wrong or either your data has a problem. Okay. So the pattern was showing when you increase the water cement ratio, the slump increases. This is what the overall data was showing. But when you made an equation out of it, it was showing water cement ratio has a negative effect on the slump. This is not true. So now you know there is a problem with the model. Okay, it was happening with me many times. Okay, and obviously I'm traffic transportation. So I usually deal with safety or traveler behavior. So once I was doing like this, and I found that there was a factor which was in the data, it was showing positive effect. But when I made the model, the coefficient of that factor became negative. Okay. So because I know the pattern, then I can check my model. Otherwise, I will show my model to someone, it will be rejected obviously. And it is useless even for me. Okay. The problem was that factor was nominal. So when I put it in the software, some software do that. Okay, so you need to be careful. It flipped the 0 to 1 and 1 to 0. I don't know why. It still does. Okay, and not only 0 to 1. If I have like 3 categories, 1 to 3, it flips all of them. Okay, there's a problem with the software. Anyways, that's why we do the programming. I'm not using software. But anyways, if I don't know the pattern, I cannot know my mistake. I cannot know what the software has done. Okay, so then I have to go back and flip every time I use the software. Make the negative as positive, positive as negative. Every time. Okay, but you cannot do it unless you know what is happening. Okay, just yesterday we had the data about asphalt, right? Asphalt. So they were putting plastic in asphalt as a replacement, recycling the plastic with asphalt. So I did the analysis, okay, and we were trying to see the relationship. Okay, so we performed one test and another test. Okay, when we performed one test, we got the same results. Another test, same results. Okay, but this one was not easy to explain, so I discarded. This one was easy to explain because it's matching with the pattern. Okay, so I kept it. Okay, and mainly because of the type of data. My type of data was I have one category of plastic, another category of plastic, third category of plastic. So when I put it in the software does this and this both. But this one is not valid for the categories. Okay, so it all comes to you understand the data and you understand the pattern of the data and so on. This can only happen once you have done this. Okay. Yeah. So this is, I don't know who that guy is. Some guy. Okay. And he said you cannot manage what you cannot measure. Okay. Manage in the sense that you cannot analyze, you cannot investigate, okay? You cannot understand something which you cannot measure. Okay. And the first step of your measurement is, can you describe it? Can you describe the data? Okay. So for example, before you start designing a foundation, you need to understand the soil properties, right? Okay. So you need a regular value, normal value, what is the average value of the soil. And you know the soil properties are not like same. You can put your testing instrument at any particular point, it will give you some variation. No? That's why they do multiple tests for soil or anything, even for concrete. They do multiple tests, right? They don't rely on one sample. So, before you start, you will collect the soil properties, okay? And before you analyze the experiment, you must describe your results, okay? How the properties are changing, what is the average value, what is the variation, the value, and so on and so forth. Okay, so again, going back to the same, I don't know, who guys don't remember that? We don't remember what we studied in travel. I can show you the slides. Exactly same. Okay, we have some values which are called as values of central tendency, measures of central tendency. Okay, so central of the data. Okay, so there are some values which can describe the central tendency of the data, the center of the data. Now keep one thing in mind. Our aim is not to get the central value, like the numeric center. We don't want the numeric center of the data. Okay. Otherwise, if you tell me my strength lies between 10 and 20 kilonewton, what is the center? 50. Do I need any analysis for that? But did you consider the values? Is this what we want? I want to know where the values are centered, not where the range is centered. Not the center of the range, the center of the value. So I am looking for the most common value. Okay, so when you consider this, keep this point in mind. We are looking for the most common value. Okay, not the range of the value. So we can use mean. Okay, another term for mean is average. Okay, are they same or different? Same. Same? Okay, both of you are wrong. Very good. There is some difference. We will not go in that detail, but there is some difference between them. Okay, the statisticians say that there is a difference between mean and average. Okay, so average, you know, average, summation upon number. Right? That is an average. Okay. Mean can be something different. Mean can be this same as average, or something different depending upon your data. If your data has a bunch of values, 100 values, you calculate the average, that is your mean, no problem. But if your data is not a bunch of values, it's a distribution, it's a frequency diagram, it's something like this, or it's composing of percentages, then your mean is different and the average is different. Okay, just to give you a rough idea. The problem with mean and average, as I already mentioned, the example with the speed data. You get one value which is very high or one value which is very low. It will destroy the data. Not the data itself, but the mean. Okay. At that one value you pull your mean towards itself, right? Okay. And normally, because this value is so high or so low, and you are putting all values equally, you are adding, right? This plus this plus this plus this. Okay. So obviously, these 20 values which are within 100, okay, will be more affected by a value which is 160. Okay. All values are less than 100, and this is 160. This 160 will have more pull towards it. And same thing here on the other side. All values are 60, and there's one value which is 10. Okay, so it will have more pull because there's a drastic change in the range, the value. So the problem with mean or average is it is very sensitive to outliers. So if you want the real mean, the real average, then you look at the outliers, you decide whether you want to keep them or clean the data, or you can go with other measures of central tendency, such as the median and the mode. Okay, the median is what? Middle value. Okay, so middle value is then not affected by the outlier. So if you are going this side or this side, but the middle remains the same. Okay, and the mode is the most repeated value. Okay, in essence, we are going after this data, this value. This is the main essence. The value which is most, another name which they give for mean, not the average, mean, is most expected value. Most expected value. Okay, this is the term which statisticians use for the mean. Okay, but only the mean, not the average. They don't use most expected for the average. Okay, but they use it for the mean. The mode is something like the most expected value, right? It is repeated more times. But the problem is, so the concept is I want the mode. This is my target. The most repeated value, the most expected value. But the problem is what? I should calculate mode every time, right? But I do not. If you see any papers, if you see any data analysis, you will not see mode. Very, very rarely you will see the mode is used or calculated. Why? Because take time to calculate. How much time? Depends on the data.
Maybe use it.
If you can get it, we will use it. Obviously. It takes more time. How much time? It can take you the whole life. The population. It's a set of random values. How would you know the mode? Yes. Okay. So mode is when the values are repeating, right? But most of the real world data is not mode based. You cannot know the frequency. How many times this value is repeated? I don't know. Okay. Most of the traffic data is like this. Most of the lab experiment data is like this. We prepare. I wouldn't want to. I was thinking, should I go in the slide mode or not? Okay, but the problem is if I go in the slide mode, then I cannot come out without stopping the recording. I will not come out. But I can show you the experimental data in which like 50 values are taken with the same mix. The design mix or the mix of the values is same proportion of everything. But the value is changing every time. Okay, and I don't know what those kids did. Kids, right? Students. They got some of the values negative. It was percentage of something in the sample. Percentage of anything in the sample cannot be negative.
If it's there, it's there.
It's there, it's there. It's not there, zero, right? Cannot be negative. So, but they got negative as well. Okay, you forget about the negative value, they must have messed it up. But all the other values are also changing. I cannot find a single repetition of the value. And I have more than 50 values. With one sample, with one mix, I have more than 50 values.
Maybe they were guessing.
Huh? No, this is real. This is real. Okay.
So we don't have
This is real. We cannot have more. The point was, going back, she forgot about the point. Yes, okay. But anyways, the experimental data itself, although it is in the laboratory, it will not give you exact same value all the time. Okay. So reporting the mean strength of the concrete standard, but if one test was a clear outlier, the median might be a better representative. Okay, so you have to select which one you want to have. Okay, so usually we depend upon mean. Okay. provided that our observations do not have many outliers. Okay, if they have outliers, then we need to consider that. Okay, then we have measures of dispersion, which tell you about the values, which tell you about the variation in the data, the range of the data, and so on. So dispersion means variation. Variation from where? What is my point of reference? From the center. Okay, variation from the center. So the first one is range. Okay, maximum minus minimum. And the range will have outliers. Right? The absolute minimum is an outlier. The absolute maximum is an outlier. So we have only one value. Unless you have, for both cases, a bunch of values. Okay, which is very rare, like I said. The absolute maximum and the absolute minimum are usually outlier. They are obviously somewhat away from the data. That's why they are the maximum and the minimum. Okay, then we have the variance. Okay, and the standard deviation. What is the difference between the variance and standard deviation?
Variance is standard deviation.
Square. Okay, variance is square, standard deviation is square root. Okay, and how do we define the standard deviation?
It's deviation
From
the central organ.
yeah. In this case, the mean. Because we are using the mean.
Plus or minus.
Yeah, we are using the mean. Okay, in this case, we can say the mean. The mean. Okay. You said the difference, right?
Yeah.
I'll just add one word here: average difference. Because we are taking difference not from one value, we are taking difference for the entire data set. Okay, so that's the average difference. Okay, and if you take this one, this is the square of the difference, average square difference. Why do you take the square? Actually, you do the square, and if you want a standard deviation, then you do the square root. Okay, so why we are taking the square? You want the difference, right? So take the difference. Why do I have to do the square and then the square root? If I want the difference, take the difference. I take the difference, then the square, and then square root. So much time. Huh? What does average has to do with taking the square and the root? Nothing. Useless, right? We shouldn't do it.
It's not useless because they are doing it.
They are doing it. Why? Why? In the undergrad, again, I don't know, but there were two equations for standard deviation. One was very simple, the other one was very difficult. Okay. Then I used to ask at that time, I asked again, which one is simple? I said this one. Which one we will use? The other one, not the simple one. Okay. We make our life difficult ourselves. Why are we making it our life difficult now? When you take the difference can be negative or positive. When you take the average, what will happen to negative and positive? They will cancel out each other. Okay. But this is not the case. A difference on this side or a difference on this side is still away from the center, right? So I need to keep it. Okay. So how do I keep it? I take the square. Okay. So, and why it is important? Because you will face this when you are designing your experiments. Okay. If I am only expecting the difference to be on one side, I'll treat it differently. Okay. But if I'm expecting the difference to be on both sides, then I cannot just leave it. I cannot just leave the values. Okay. So there are two things you can do. One is taking the square, the other one is taking absolute. Okay. A square for differences, for errors, is a more strong approach. Taking the square is a stronger approach when you talk about the differences and the errors. So standard deviation is sort of an error, right? It's away from the standard. Okay. So when you are dealing with errors, okay, or variation in the data, so we want to keep the differences. We don't want them to cancel out. Either you can take an absolute or a square. Okay. In these cases, we prefer to take the square. It's a more stronger approach. Why? Because a square will, if you take the square of a very small term, what will happen? It will become small, right? And if you take the square of a very big term, it will become a lot bigger, right? Okay, so it has a compensating effect. If you take absolute, what will happen? Small will remain small, big will remain big. Same scale. But taking the square extends your scale. So a bigger difference will have more impact on the standard deviation, and a smaller difference will have less impact on your standard deviation. Okay, same thing with that. If I'm calculating error, it can be positive or negative, right? Error can be positive or negative. So should I take absolute of the error or the square of that? Square is much stronger. We take absolute as well, no problem. You can. But taking the square is much stronger because it will highlight the bad values. Okay, it will create more impact of bad values. Okay, so a standard deviation and the variance, and then we have something which we call as coefficient of variation, in which you combine dispersion as well as central tendency. So this is how we calculate coefficient of variation. A standard deviation upon mean. Okay, and then we convert it to percentage. So coefficient of variation is normally taken as percentage. Okay. So it tells you the variation with respect to mean. With respect to mean. Okay. Usually, this coefficient of variation should not reach 100% or more.
Yeah.
The coefficient of variation should not reach 100%
This
or
means
more.
that this means that the standard deviation is very close to very increased.
Standard deviation should be. Say again.
If it reaches 200, this means that standard deviation is same as
Same as mean or bigger than mean.
yeah,
Because
which means
data is
that
far, far away from the mean itself. Okay? And in some cases, it doesn't make any sense. Because, for example, speed or strength. That's it. Okay? So mean speed is 48. If a standard deviation is more than 48, what does it mean? Standard deviation was what? Difference, right? So if it is 50, your mean is 48. The difference is 50. So 48 minus 50. Okay. In some cases it will not make any sense. It can, obviously, you are not taking values, you are doing the square and everything. But in the end, when you interpret it, it doesn't make any sense. Okay. So it should be less than 100%. In some cases, we used it for structures data, beam testing data. You know Dr. Shah, right? Okay, so he had this data and we were calculating coefficient of variation for the error, not the values, the error. The mean error and the standard deviation of the error. Okay. So our goal was to reach 100%. So the mean of the error, the standard deviation of the error, our goal was not to exceed 100%, but to be close to 100%. Close to 100% means that your mean error and the variation in the error are same. Okay, which is a good thing. Okay, the error is distributed. Okay, in other words, there are no outliers in your error, which is good. Anyways. So, for example, a standard deviation of 2 megapascal on a 40 megapascal strength concrete. 40 is the mean then. Okay, and standard deviation of 2 in this much is low precision. Okay, as compared to if you have so 2 megapascal in 40 megapascal is more precise. It's a very lower value, right? If you calculate coefficient of variation in this case, okay, how much will it be? 2 upon 40? And the same here, if it is 2 megapascal and 10,
20.
then it will be 22. It was written. So now you know why we are saying coefficient of variation. In both cases, you see the standard deviation is same. But in this case, it means more, variation. The same value can mean more variation in two different data sets. So that's why we need the coefficient of variation. Okay, if you just deal with standard deviation, you will see 2 here and 2 there. Okay, fine, they are same. And both of them are concrete. Okay, but in the first case, it's very low. Second case, very high. Okay, how many times? 4 times higher, right? So, okay, you have this data, right? We used it last time, the same data set. Okay, so for example, if you want to calculate the descriptive statistics for this data set. So what descriptive statistics we are calculating? We are calculating mean, median, and SDS, what? Standard deviation. Okay. Then we can use this function dp layer, okay, to summarize the data for all variables. So the first one will calculate it for each variable in the data. Okay, for strength and the strength basically. So we are calculating mean, median, mode for the strength. So if you open the file, you will see there are different variables. So the first case will do it for each variable at a time. For the second case, the dp layer function will do it for the entire data set at the same time. So go ahead. To use this, because you are using it for the first time, so like you need to import the, when you run this command, it will import the library, this one. So it's a tool. It will import this tool and then it will